When we look at a clock, it feels like we are looking at time itself. The second hand moves, numbers change. Digital displays tick forward in perfect rhythm. It gives us the impression that time is something solid and independent, something that exists on its own and flows steadily whether we pay attention to it or not. But Richard Feynman challenged this ordinary assumption. He invited us to ask a deeper question: what is a clock actually measuring? A clock does not measure time in the way a ruler measures length. A ruler can be placed next to an object and compared directly. But time is not something you can place next to anything. A clock measures motion. A pendulum swings back and forth. A quartz crystal vibrates at a precise frequency. An atomic clock measures transitions between energy levels in atoms. In every case, what we call time is simply a repeating physical process. This means something important. Time is defined through change. If nothing changed in the universe, if no particles moved, no atoms vibrated, no light traveled, then there would be no meaningful way to measure time at all. Without change, the concept of time loses its operational meaning. Feynman often emphasized this operational view of physics. Instead of asking what time is, in some abstract philosophical sense, he would ask how we measure it and how it behaves in experiments. Imagine a world in which everything slows down at exactly the same rate. Your heart beats more slowly. Your thoughts process more slowly. Every clock ticks more slowly. Every atomic vibration decreases in frequency. Would you notice? The surprising answer is no. Because all comparisons are relative, you would have no reference to detect the change. Your sense of 1 second would feel exactly the same. This simple thought experiment reveals that time is not an absolute external flow. It is always tied to comparisons between processes. For centuries, the dominant view, especially after Isaac Newton, was that time flows uniformly and independently of the physical world. Newton described time as absolute, true, and mathematical, flowing equably without relation to anything external. In that picture, the universe exists inside a kind of invisible cosmic clock that ticks the same everywhere. But Feynman explained that modern physics does not support this view. Time is not separate from the physical processes of the universe. It is woven into them. When you define a second, you are defining it in terms of something happening repeatedly. Today, the official definition of a second is based on the vibration frequency of a cesium atom. That means our most precise measurement of time depends on atomic behavior. If the laws governing atoms were different, our second would be different. This reveals a subtle but powerful truth. Time is not something we observe directly. We infer it from motion and change. We never see time itself. We see clocks changing. We see the sun rise and set. We see shadows shift. We see hands moving across a dial. These are all physical processes. Time is the framework we use to describe and compare them. Feynman also liked to point out that our intuition about time comes from everyday human experience. We evolved at speeds much slower than the speed of light and in gravitational fields that are relatively weak. Under those conditions, time appears steady and universal. But physics tells us that this stability is only approximate. At very high speeds or near massive objects, the ticking of clocks changes. Even before diving into relativity, the idea that clocks measure processes already hints that time cannot be completely independent. If time were truly separate, then all clocks would always tick in perfect synchrony regardless of their conditions. But experiments show that this is not the case. Move a clock fast enough, and it ticks differently. Place it in a stronger gravitational field, and it ticks differently. This forces us to rethink what we mean when we say, 1 hour has passed. 1 hour, according to which clock? Under what conditions? Compared to what process? Feynman encouraged people not to be intimidated by these questions. He believed confusion was a healthy sign. When something feels strange, it means we are confronting a limitation in our intuition. The fact that time behaves differently than our common sense expects is not a flaw in physics. It is a clue that reality is deeper than our everyday experience. Consider two identical clocks placed side by side. They tick together perfectly. Now imagine one of them is placed on a fast, moving spaceship while the other remains on Earth. When the spaceship returns, the clocks no longer agree. The traveling clock shows less elapsed time. This is not because the clock malfunctioned. Every physical process on the spaceship slowed down relative to Earth, including the aging of the astronaut. If a clock simply measures internal motion, and motion itself changes under different conditions, then time as measured by that clock changes too. There is no master clock outside the universe to settle the disagreement. Each clock faithfully measures its own physical processes. This challenges the comforting idea that time is a universal background against which events unfold. Instead, time becomes something local and physical. It is part of the system, not an external stage. Another way to see this is to ask how we synchronize clocks. To say two clocks show the same time, we must send signals between them, usually light signals. But light travels at a finite speed. This means synchronization itself depends on the laws of physics. There is no instantaneous cosmic signal that sets every clock in the universe simultaneously. Even defining at the same time becomes complicated once we realize signals take time to travel. Feynman appreciated the humility this brings. We often speak casually about time passing, but physics reveals that what we really mean is that systems evolve according to laws. The ticking of a clock is just one evolution among many. Time is our way of organizing these changes into a coherent description. In everyday life, it is practical to think of time as steady and universal. Our schedules depend on it. Our technology relies on consistent standards, but at a deeper level, time is not a substance flowing independently through the universe. It is a measure of change, defined by physical processes, and shaped by the laws governing motion, light, and energy. When you next look at a clock, you are not seeing time itself. You are seeing a physical system undergoing regular change. The meaning of that change, and how it compares to other changes elsewhere, depends on the structure of the universe. That realization alone transforms time from something obvious into something extraordinary. For most of human history, time was assumed to be absolute. It was believed to flow the same way everywhere, for everyone, under all conditions. This idea was formalized by Isaac Newton, who described time as something that exists independently of the world. In Newton's universe, time ticks uniformly, unaffected by motion, gravity, or the observer. Whether you are standing still, riding a horse, or traveling across the ocean, 1 second is always 1 second. The universe operates inside this steady, invisible framework. This picture feels natural because it matches everyday experience. When two people compare their watches after walking in the same city, they agree. When a train moves at ordinary speeds, passengers do not notice their clocks slowing down. Everything appears synchronized. For centuries, this reinforced the belief that time is universal and absolute. But at the beginning of the 20th century, Albert Einstein overturned this deeply rooted assumption. His theory of relativity revealed that time is not fixed. It depends on motion and gravity. Richard Feynman had a remarkable ability to explain just how radical this shift was. He showed that relativity is not just a small correction to Newton's ideas. It is a complete transformation in how we understand reality. The turning point begins with the speed of light. Experiments in the late 19th century showed something puzzling. No matter how fast you move, the speed of light in a vacuum remains constant. If you shine a flashlight while standing still, you measure the speed of light as about 299,792 kilometers per second. If you shine it while running forward, you still measure exactly the same speed. Even if you could travel near the speed of light itself, the beam would still move away from you at that same speed. This result is completely different from how everyday speeds work. If you throw a ball forward while standing still, it moves at a certain speed. If you throw it while running, its speed increases relative to the ground. Speeds normally add together. But light refuses to follow this rule. Einstein realized that if the speed of light is truly constant for all observers, then something else must change. That something is time. Imagine two observers, one standing on a platform and another moving past on a fast train. Each carries a clock. According to classical thinking, both clocks tick at the same rate. But if the speed of light must remain constant for both observers, then their measurements of time cannot be identical. To preserve the constancy of light, time itself must stretch or compress depending on motion. This effect is known as time dilation. A moving clock ticks more slowly compared to a stationary one. The faster you move, the slower your clock runs relative to someone at rest. This is not a trick of perception. It is a measurable physical effect. Experiments using precise atomic clocks have confirmed it repeatedly. When clocks are flown on airplanes and compared to identical clocks on the ground, they show small but real differences in elapsed time. Feynman emphasized that nothing is wrong with the moving clock. It does not malfunction. Every process inside that system slows down equally: heartbeats, chemical reactions, atomic vibrations. From the perspective of the moving observer, everything feels normal. Their own clock seems steady. It is only when comparing with another observer that the difference becomes clear. This destroys the idea of universal simultaneity. In Newton's universe, if two events happen at the same time for one observer, they happen at the same time for everyone. Relativity shows this is not true. Two lightning strikes that appear simultaneous to someone standing on a platform may not appear simultaneous to someone moving past them at high speed. To understand why, consider how we decide whether two events are simultaneous. We rely on light signals. If light from both events reaches us at the same time and we are equally distant from them, we conclude they occurred simultaneously. But if another observer is moving relative to us, the distances and timing of light signals differ. Because the speed of light is fixed, differences in motion lead to differences in time measurement. Feynman loved explaining that this is not philosophical speculation. It follows directly from simple, experimentally verified principles. If you accept that the laws of physics are the same in all inertial frames, and that the speed of light is constant, then time cannot remain absolute. The mathematics leaves no alternative. Relativity also introduced another dramatic idea. Time and space are not separate entities. They are woven together into a four-dimensional structure called spacetime. Events are described not just by where they happen, but when they happen. Different observers moving relative to each other slice spacetime differently. What one observer calls now may include events that another observer considers part of the past or future. This does not mean anything goes or that causality breaks down. The order of cause and effect remains consistent. If one event directly causes another, all observers agree on that order. But events that are not causally connected can have different temporal orderings depending on the observer's motion. The revolution becomes even more striking when gravity enters the picture. Einstein's general theory of relativity shows that massive objects curve spacetime. This curvature affects the passage of time. Clocks closer to massive objects tick more slowly than clocks farther away. This effect has also been experimentally confirmed. Even a clock placed at sea level ticks slightly slower than one placed on a mountain because it is deeper in Earth's gravitational field. Feynman was particularly skilled at helping people accept these ideas without mysticism. He would say that nature behaves this way whether we find it comfortable or not. The role of physics is not to preserve our intuition, but to describe reality accurately. The death of absolute time does not make the universe chaotic. Instead, it reveals a deeper order. The laws of physics remain consistent and precise. What changes is our understanding of how measurements depend on the observer's state of motion and gravitational environment. In everyday life, the differences predicted by relativity are extremely small because our speeds are tiny compared to the speed of light, and Earth's gravity is relatively weak. That is why Newton's concept of time works so well in ordinary situations. It is an approximation that becomes inaccurate only under extreme conditions. But once we step into high-speed space travel, powerful gravitational fields, or precise technological systems like GPS satellites, relativity becomes essential. GPS satellites orbit Earth at high speed and experience weaker gravity than clocks on the surface. Both motion and gravity affect their clocks. Engineers must correct for these relativistic effects, or navigation systems would quickly become inaccurate. The realization that time is not universal, but relative to motion and gravity, reshapes our understanding of existence. There is no single cosmic clock governing the universe. Each observer carries their own measure of time, influenced by their movement and position in spacetime. Through relativity, the steady ticking of Newton's universe gives way to a dynamic and flexible reality. Time bends, stretches, and depends on perspective, and yet the laws behind it are elegant and consistent. This was the revolution Einstein began, and one that Feynman helped generations truly understand. When Einstein's theory of relativity reshaped physics, it did more than alter our understanding of time. It dissolved the boundary between space and time entirely. Instead of treating them as two separate things, space as the stage and time as the ticking clock, modern physics reveals that they are woven together into a single structure known as spacetime. Richard Feynman had a gift for guiding people through this transformation without losing them in abstract mathematics. He showed that spacetime is not just a scientific term, but a profound shift in how we understand reality itself. In everyday thinking, space and time feel completely different. Space is where things are. It has length, width, and height. You can move left or right, forward or backward, up or down. Time, on the other hand, feels like a one-way flow. You move from past to future, and you cannot reverse direction. Because of this difference, it seems natural to treat them separately. But relativity forces us to reconsider that separation. If time slows down when you move fast, and distances shrink in the direction of motion, then space and time cannot be independent. They must be connected in a deeper way. To understand this, Imagine describing an event. Suppose a star explodes. To fully describe that explosion, you must specify not only where it happened, but also when it happened. A location without a time is incomplete. A time without a location is equally incomplete. Every physical event requires 4 coordinates, 3 for space and 1 for time. Hermann Minkowski, Einstein's former mathematics professor, realized that relativity makes the most sense if we treat these 4 coordinates as parts of a single 4-dimensional structure. He famously said that space by itself and time by itself are doomed to fade away into mere shadows, and only a union of the two will preserve independent reality. That union is spacetime. Feynman explained this idea in a practical way. Instead of imagining time as something separate, picture the universe as a vast 4-dimensional fabric. Every event, every heartbeat, every collision of particles, every flash of light exists at a specific point in this fabric. The history of any object can be traced as a path through spacetime. This path is called a world line. If you stand still, your world line moves mostly in the time direction. You are not traveling through space much, but you are always moving forward in time. If you walk across a room, your world line tilts slightly, combining motion through space with motion through time. If you could travel near the speed of light, your world line would tilt dramatically. Here is where the unity of space and time becomes essential. In classical physics, space and time are fixed and separate. In relativity, the division between them depends on the observer. 2 observers moving relative to each other will disagree about how to split spacetime into space and time. What one observer calls a difference in time, another might partly interpret as a difference in space. This is not just a trick of words, it has measurable consequences. Consider 2 events occurring at different places. One observer may say they happened at the same time, but in different locations. Another observer, moving at high speed, may say they happened at different times. Both are correct within their own frame of reference. The disagreement arises because they slice spacetime differently. An analogy may help. Imagine a loaf of bread representing spacetime. Each slice represents all of space at a single moment in time, according to a particular observer. A stationary observer slices the loaf straight across. A moving observer slices it at an angle. The slices are different, but they come from the same loaf. There is no single, universal slice that represents now. For everyone, Feynman appreciated how strange this sounds. It means that the present moment is not universal. There is no cosmic now, shared by the entire universe. Instead, each observer has their own version of simultaneity, determined by their motion. Spacetime also changes how we understand gravity. In Einstein's general theory of relativity, gravity is not a force pulling objects together in the traditional sense. Instead, massive objects like stars and planets curve the fabric of spacetime itself. Objects moving nearby follow the curved paths in this geometry. Feynman explained that objects are not being pulled in the usual sense. They are simply following the straightest possible paths in a curved spacetime. Just as a marble placed on a curved surface will roll along a path determined by that surface, planets move along paths determined by the curvature caused by massive bodies. This curvature affects time as well as space. Near a massive object, time passes more slowly compared to regions farther away. The geometry of spacetime determines how clocks tick and how rulers measure distance. Time and space are no longer fixed backgrounds. They are dynamic and influenced by matter and energy. One of the most striking consequences of spacetime is the idea of light cones. Because nothing can travel faster than light, events in spacetime are divided into regions. The light cone of an event represents all the possible locations that light from that event can reach. Events inside the future light cone can be influenced by the original event. Events outside cannot, because that would require faster than light communication. This structure preserves causality. Even though observers may disagree about the timing of distant events, they will always agree about cause and effect. If event A causes event B, then B must lie inside A's future light cone. The geometry of spacetime enforces this rule. Feynman often reminded people that while these ideas are abstract, they are grounded in experiment. Time dilation, length contraction, gravitational time shifts. All of these have been tested and confirmed. Spacetime is not just a mathematical invention. It is the framework that accurately describes how nature behaves. Perhaps the most profound shift spacetime introduces is the idea that the universe is not evolving inside time in the way we once imagined. Instead, the universe simply is a vast four-dimensional structure containing all events. Our experience of moving through time may reflect how our consciousness travels along our world line, moment by moment. Whether or not one accepts that interpretation, the scientific message is clear. Space and time are inseparable. They form a unified geometry that determines how motion, gravity, and causality work. What feels like separate dimensions in daily life are, at a deeper level, different aspects of a single structure. Through clear reasoning and fearless curiosity, Feynman helped people see that spacetime is not mystical or poetic. It is the natural outcome of taking experimental facts seriously. Once we accept that the speed of light is constant and that the laws of physics are the same for all observers, spacetime emerges as the only consistent way to describe reality. In this framework, time is no longer a lone river flowing through the cosmos. It is one direction within a vast geometric landscape inseparable from space, shaped by matter, and fundamental to the structure of the universe itself. If the fundamental laws of physics do not prefer a direction of time, then why does time seem to move only forward? Why do we remember yesterday but not tomorrow? Why does a glass fall and shatter, but shattered pieces never leap up and reassemble themselves? This puzzle lies at the heart of what physicists call the arrow of time, and it is deeply connected to the concept of entropy. Richard Feynman had a powerful way of explaining that the direction we experience in time is not built into the basic equations of motion, but emerges from statistical behavior on a large scale. At the microscopic level, many physical laws are time-symmetric. If you record two particles colliding and then play the film backward, the reversed motion still obeys the same physical laws. Newton's equations work equally well forward or backward. The equations of electromagnetism do not demand a preferred direction of time. Even in quantum mechanics, the core mathematical framework allows processes to unfold in either temporal direction. Yet our daily experience strongly contradicts this symmetry. We never see smoke gather back into a cigarette. We never see heat spontaneously flow from cold objects to hot ones. These everyday processes clearly have a direction. Something is distinguishing past from future. The key to this distinction lies in thermodynamics, especially the second law. This law states that in an isolated system, entropy tends to increase. Entropy is often described as a measure of disorder, but that word can be misleading if taken too casually. A more precise way to understand entropy is in terms of probability. Entropy measures how many microscopic arrangements correspond to a given macroscopic state. Consider A simple example: a box divided into two compartments by a removable barrier, with gas molecules confined to one side. When the barrier is removed, the gas spreads out to fill the entire box. It never spontaneously gathers back into one compartment. Why? Because there are vastly more ways for the molecules to be spread out than for them to be concentrated on one side. The spread out state is overwhelmingly more probable. Nothing in the microscopic laws forbids the molecules from randomly returning to one side. In principle, it could happen, but the probability is so unimaginably small that we never observe it in practice. The direction of time we experience is tied to this overwhelming statistical tendency toward more probable configurations. Feynman explained that the arrow of time is not a separate law imposed on the universe. It is a consequence of starting conditions. The universe began in a state of extraordinarily low entropy. That means it was highly ordered compared to the enormous number of ways its particles could have been arranged. From that special beginning, entropy has been increasing ever since. This gradual increase creates the direction we call forward. Broken glasses, melting ice, mixing cream into coffee. These are all processes in which entropy increases. They move from less probable states to more probable ones. The connection between entropy and memory is particularly fascinating. When you remember something, your brain undergoes physical changes. Neurons form connections. Chemical reactions occur. Energy is consumed. Heat is released into the environment. These processes increase entropy overall. Memory formation is itself an irreversible physical process. This explains why we remember the past but not the future. The past corresponds to lower entropy states that have evolved into higher entropy ones. The traces of those lower entropy configurations are stored in records, photographs, fossils, written notes, neural connections. The future, by contrast, consists of configurations that have not yet formed such records. In a sense, memory flows in the same direction as entropy. Feynman emphasized that if entropy were decreasing, our perception of time would reverse as well. In a hypothetical universe where disorder steadily decreased, observers within it would perceive their own direction of time as forward, even though from our perspective it would appear reversed. The arrow of time is not something absolute. It is tied to thermodynamic behavior. This raises a profound question: why did the universe start in such a low entropy state? That remains one of the deepest mysteries in physics. The early universe, shortly after the Big Bang, was extremely hot and dense, but also remarkably uniform. Paradoxically, this uniformity represents low entropy in a gravitational context. As the universe expanded, gravity caused matter to clump into stars and galaxies, increasing entropy further. The second law of thermodynamics gives time its direction, but it does so statistically, not absolutely. On small scales, fluctuations can occur where entropy temporarily decreases. In tiny systems of particles, random variations can briefly create more ordered states. But on the large scales of everyday life, the probability overwhelmingly favors increasing entropy. One way to visualize this is to imagine a deck of cards. A brand new deck in perfect order is a highly specific arrangement. There are very few ways to achieve that exact order, but there are astronomically many ways to shuffle the deck into random sequences. If you shuffle the cards repeatedly, they quickly become disordered. The transition from order to disorder is simply moving from an unlikely configuration to one of many likely configurations. Time's arrow, then, is a reflection of probability. We move from special states to generic ones. from structure to randomness, from concentration to dispersion. Feynman had a talent for stripping away the illusion of mystery without diminishing the wonder. He would point out that while entropy explains the direction of time in practical terms, it does not eliminate the strangeness of the situation. The microscopic laws do not demand this direction. It emerges from initial conditions and statistical reasoning. Another important aspect is that entropy is connected to information. A low-entropy system contains more usable information about its detailed arrangement. As entropy increases, information about precise configurations becomes effectively lost. When cream mixes into coffee, the detailed positions of molecules become scrambled beyond recovery. This loss of recoverable information is another way of understanding irreversibility. The arrow of time is therefore not an independent force pushing the universe forward. It is a pattern arising from the interplay between probability, initial conditions, and large numbers of particles. The reason we cannot unscramble an egg is not that physics forbids it, but that the number of scrambled states vastly outnumbers the unscrambled ones. In this light, time's direction is not written into the core equations of motion. It emerges from statistics and the history of the cosmos. The steady march from past to future that defines human experience is rooted in entropy's relentless increase. What feels like a fundamental property of existence may, at its core, be a consequence of probability and beginnings, a cosmic story unfolding from an improbably ordered start toward ever greater disorder. When we step into the quantum world, our classical intuition about time begins to falter completely. At the scales of atoms, electrons, and photons, the familiar rules of everyday experience no longer apply. Richard Feynman, one of the pioneers of quantum mechanics, had a remarkable ability to guide people through this strange territory, showing that even time itself behaves in ways that defy ordinary understanding. In classical physics, time is a smooth, continuous flow. Events unfold in a clear sequence. Causes lead to effects, clocks tick steadily, and we can trace the motion of particles along predictable paths. Quantum mechanics, however, reveals that at the microscopic level, these assumptions break down. One of the first surprises of quantum mechanics is that particles do not have precise positions and velocities at the same time. Heisenberg's uncertainty principle tells us that the more accurately we know a particle's position, the less accurately we can know its momentum, and vice versa. In classical physics, knowing both allows us to predict the future exactly. In quantum mechanics, such determinism vanishes. The future is inherently probabilistic. Time still exists as a parameter in the equations, but the behavior of particles within that timeline is no longer fixed. Feynman emphasized that in quantum mechanics, we must think not about single paths or trajectories, but about possibilities. A particle traveling from one point to another does not follow one unique path. Instead, it simultaneously explores every conceivable path connecting the 2 points. This idea, now called the path integral formulation, was Feynman's revolutionary contribution. To predict where the particle will be detected, we sum over all possible histories, each path contributing with a certain probability amplitude. This is not just abstract mathematics. It captures the actual behavior of quantum systems. From the perspective of time, this multiplicity of paths is astonishing. Imagine you want to know how an electron moves from point A to point B. Classically, there is a single, continuous trajectory. Quantum mechanically, there are countless trajectories, some forward, some curving, some looping back in ways that seem impossible in our everyday world. Time in quantum mechanics is no longer a simple sequence along which particles march. It becomes a landscape of possibilities, with each path weighted and interfering with others. Feynman's diagrams, another of his brilliant innovations, make this even clearer. In these diagrams, time is typically represented along one axis, and particles are shown as lines moving through it. Interactions, such as collisions or the emission of photons, are represented as vertices where lines meet. These diagrams allow physicists to calculate probabilities of events with remarkable precision. But there's a subtle twist. In certain interpretations, some lines can be mathematically viewed as representing particles moving backward in time. At first, this seems like science fiction. How could a particle travel backward through time? Feynman himself was careful to clarify that this does not imply macroscopic backward causation. Eggs do not unscramble, and you do not see bullets return to guns. Rather, this is a feature of the equations used to describe quantum interactions. In fact, what we call an antiparticle like a positron, the antimatter counterpart of the electrons, can be mathematically treated as an electron moving backward in time. This symmetry is built into the mathematics of quantum field theory and allows calculations to remain consistent and elegant. This idea highlights a fundamental truth. At the quantum level, time does not have the rigid, one-way character that our classical intuition suggests. The equations themselves are largely symmetric with respect to time. A process running forward in time has a valid mathematical counterpart running backward. What distinguishes past from future in our experience emerges not from the microscopic laws themselves, but from boundary conditions, statistical behavior, and interactions on larger scales. Another striking consequence of quantum mechanics is the way it blurs the distinction between cause and effect. In classical physics, causality is simple. One event leads to another in a well-defined order. In quantum mechanics, while overall causality is preserved, individual events are probabilistic. When an atom emits a photon, the exact moment of emission cannot be predicted. We can only assign probabilities. The sequence of events is clear statistically, but not deterministically. Time remains a parameter, but the path along it is uncertain. Feynman also showed that these quantum peculiarities have real-world consequences. Quantum tunneling, for instance, allows particles to pass through barriers they should not be able to surmount classically. This process does not require a violation of causality or time symmetry, but it demonstrates that events at the quantum level are not confined to classical intuitions of time and space. Particles explore possibilities simultaneously, constrained only by the laws of quantum mechanics. Moreover, quantum entanglement introduces further complexity. Two particles that have interacted can remain correlated over vast distances. A measurement performed on one particle instantaneously influences the probabilities associated with the other, regardless of spatial separation. While this does not allow faster than light communication or reversal of time, it challenges the classical notion of a strict, local sequence of cause and effect. Time and causality become probabilistic, intertwined with correlations that defy everyday reasoning. Feynman's genius was not only in uncovering these phenomena, but in showing how they fit together coherently. The seeming strangeness of quantum mechanics does not signal chaos. Rather, it reflects a deeper order in which time is a flexible and sometimes counterintuitive parameter. Time in the quantum world is not a simple line along which particles march. It is a canvas upon which probabilities evolve, paths interfere, and possibilities coexist. Even more, the combination of quantum mechanics with relativity deepens the mystery. When high-speed motion or strong gravitational fields are involved, time is not only flexible due to relativistic effects, but also uncertain due to quantum effects. Feynman's framework allows these layers to coexist, offering a consistent, predictive model even in situations where classical intuition fails completely. Ultimately, what Feynman teaches us is that our everyday experience of time, linear, unidirectional, predictable, is an emergent property. At the microscopic scale, time is a landscape of possibilities, symmetric in its fundamental equations, and intimately connected with probability. What we perceive as past, present, and future is a macroscopic approximation arising from countless quantum events and statistical behavior. By embracing this perspective, we gain not only a deeper understanding of the quantum world, but also a richer appreciation of the nature of reality. Time is not just a simple river flowing uniformly. It is a complex, multidimensional phenomenon, flexible, probabilistic, and intertwined with the very fabric of existence. Through Feynman's insights, we glimpse a universe far more intricate than our daily experience suggests, where time behaves in ways both strange and profoundly beautiful. Richard Feynman had an extraordinary ability to take the most abstract and counterintuitive ideas in physics and make them accessible, even for concepts as complex as the behavior of particles and the flow of time. One of his most brilliant contributions to understanding these phenomena was the invention of Feynman diagrams. These diagrams are not just visual aids. They are a revolutionary tool that allows physicists to calculate and visualize interactions in quantum mechanics, particularly in quantum electrodynamics, the theory describing how light and matter interact. Importantly, they also give us a way to see time in physics in a sense that is much more flexible and nuanced than the linear time of classical intuition. At first glance, a Feynman diagram looks deceptively simple. Lines represent particles, and points where lines meet, called vertices, represent interactions. Time is usually drawn along one axis, often the horizontal, while space is drawn along the vertical axis. An electron might be depicted as a straight line moving forward in time, while a photon it emits or absorbs is shown as a wavy line connecting points along that timeline. These diagrams allow us to calculate probabilities of outcomes in particle interactions with incredible accuracy. What seems like a simple sketch is actually a precise representation of complex mathematics, encoded visually. What makes these diagrams revolutionary is how they transform our understanding of motion and interaction through time. In classical physics, a particle has a well-defined path through space and time. You can predict its position and velocity, and the trajectory is smooth and continuous. In quantum mechanics, as Feynman showed, this is no longer true. Particles explore all possible paths between 2 points, each with a probability amplitude contributing to the final outcome. Feynman diagrams provide a way to visualize these possibilities. Each line in a diagram represents a potential history, and each vertex represents a point where choices are made, where probabilities branch and combine. One of the most striking insights from these diagrams is the notion that particles can, mathematically, move backward in time. Feynman showed that an antiparticle like a positron can be interpreted as an electron traveling backward through time. This does not mean that in our macroscopic world, someone will see objects reversing their course. It is a feature of the mathematical framework that makes calculations consistent and elegant. But it challenges our intuition. It shows that time in the quantum realm is not strictly linear. Particles and antiparticles are deeply connected through this symmetry, and their interactions can be treated as if time itself can be reversed at the fundamental level. Another powerful aspect of Feynman diagrams is their ability to represent complex interactions compactly. Consider an electron scattering off another electron. Classically, we might try to calculate this using forces and trajectories, but the calculations become extraordinarily complicated in quantum mechanics. Using Feynman diagrams, we can break the interaction into simpler components. The electrons exchange photons, represented by wavy lines. Each diagram corresponds to a term in a sum, which allows physicists to systematically compute the probability of different outcomes. Time, in this sense, is a bookkeeping device, a way to organize these possibilities along a dimension that can be manipulated mathematically without losing predictive power. Feynman's approach also demonstrates the interplay between determinism and probability. Time in classical physics seems like a rigid line along which events unfold predictably. Feynman diagrams show that at the quantum level, time is a canvas for possibilities. Each path, each interaction vertex, is a potential contribution to the final result. The diagrams do not depict a single predetermined history. They encode the sum over histories that gives rise to measurable outcomes. Time, then, becomes not a strict arrow, but a framework in which multiple histories coexist and interfere. These diagrams also help make sense of phenomena that otherwise appear mysterious. Processes like particle creation and annihilation, the spontaneous emission of photons, and quantum fluctuations can all be represented in a Feynman diagram. By treating time as a flexible axis along which probabilities evolve, Feynman gave physicists a way to see the dynamic structure of the quantum world. The interactions are not random chaos. They are governed by precise mathematical rules that these diagrams make tangible. Importantly, Feynman diagrams bridge abstract mathematics and physical intuition. They allow physicists to visualize interactions in a way that calculations alone cannot. By plotting events along a time axis, we see the flow of possibilities, the branching and recombining of histories, and the elegant symmetry of particles and antiparticles. In doing so, they illuminate the strange and flexible nature of time at the quantum level. Through Feynman diagrams, we also gain insight into a deeper philosophical idea, that time, while familiar in everyday life as linear and unidirectional, is far more subtle at fundamental scales. The diagrams encode the symmetries and possibilities that underpin reality, showing that time in physics is not merely a backdrop, but an integral component of the structure of interactions. Forward, backward, branching, and converging paths coexist in the formalism, reflecting the profound richness of temporal behavior in the quantum universe. Feynman's genius lay not just in the diagrams themselves, but in how they change the way we conceptualize time. They transform time from a fixed, absolute background into a dynamic, flexible dimension in which the quantum world unfolds. They reveal that events, possibilities, and symmetries are interconnected in ways that classical intuition could never capture, allowing us to understand the quantum world with clarity and precision. In this way, Feynman diagrams do more than simplify calculations, they reshape our very understanding of time and interaction in the universe. When we ask what time really means for our reality, we are confronting one of the deepest questions in physics, philosophy, and human experience. Richard Feynman had a remarkable talent for taking these questions, often abstract, sometimes baffling, and showing that they are not only meaningful but approachable through the lens of science. What he revealed is that time is not a simple, universal flow measured by a clock on the wall. It is deeply tied to the structure of the universe, the behavior of matter and energy, and the way we perceive the world around us. At first glance, time seems straightforward. Seconds tick by, days pass, seasons change. We mark birthdays, anniversaries, and deadlines. Human life is governed by the sense of past, present, and future. We plan ahead because we trust that tomorrow will follow today. This everyday intuition, though practical, is only a superficial understanding of time. The deeper reality is far more nuanced and fascinating. Modern physics reveals that time is inseparable from the structure of the universe itself. Einstein's relativity showed that time and space are part of a four-dimensional continuum called spacetime. This means that time is not independent. It is intertwined with the geometry of space and affected by the distribution of matter and energy. Clocks tick differently depending on their velocity and gravitational environment. Near a massive object, time slows down relative to distant observers. Moving close to the speed of light, time stretches. What we perceive as 1 second is therefore not universal, but depends on context. Even more radically, at the quantum level, time is probabilistic. Richard Feynman's path integral formulation revealed that particles do not follow a single path from one point to another. Instead, they explore every possible path simultaneously, and their behavior is determined by the interference of these possibilities. In this sense, time is not a rigid, unidirectional line, but a landscape of potential histories. Feynman diagrams, his brilliant visual tool, allow us to see this landscape, showing particles moving forward and backward through time, interacting in ways that challenge our classical intuition. Time is also intimately connected to the concept of entropy, which gives rise to the arrow of time. While the fundamental laws of physics are largely time-symmetric, our experience is not. We remember the past but not the future. We see broken glasses, not unbroken ones reassembling. This asymmetry arises from the statistical behavior of large numbers of particles and the universe's initial low entropy state. The forward flow of time, as we perceive it, is an emergent property of these conditions, not a fundamental law written into the equations of motion. Feynman emphasized that these ideas do not diminish the reality of time, they enrich it. Time is both a parameter in equations and a physical quantity measured by change. It organizes events, gives structure to interactions, and allows us to make predictions. Yet it is flexible, context-dependent, and deeply intertwined with the cosmos. Our everyday perception of a uniform, absolute time is an approximation that works well at human scales, but it breaks down in extreme conditions, near light speed, near massive bodies, or at the quantum scale. This understanding has practical consequences. Technologies like GPS would fail if they ignored relativistic time effects. Satellites orbiting Earth experience slightly faster passage of time than clocks on the ground due to weaker gravity and orbital speed. Engineers must account for these differences to ensure accurate navigation. Even though the discrepancies are tiny, they accumulate quickly, illustrating that time is not merely a human construct, but a measurable physical quantity with real-world implications. Moreover, time shapes our experience and consciousness. Our memories, decisions, and actions all unfold along the temporal dimension. Neuroscience shows that memory formation is a physical process, consuming energy and increasing entropy, which links our psychological experience of time to the physical world. The sense of past and future is tied to irreversible processes, the accumulation of information, and the statistical direction imposed by entropy. Feynman's insights also invite us to question what reality really means. If time is flexible, probabilistic, and emergent, then our intuitive notion of reality as a sequence of fixed events is limited. Instead, reality is a web of interacting possibilities, constrained by physical laws, shaped by space-time geometry, and unfolding according to probabilistic rules at the quantum level. Our perception of time as steady and universal emerges from this complex interplay. Ultimately, Feynman teaches us that time is not just something we passively experience. It is a fundamental aspect of the universe, deeply woven into the behavior of matter, energy, and information. It is a flexible, multidimensional feature of reality, intimately connected to causality, probability, and change. While our everyday clocks and calendars provide a convenient framework, the underlying nature of time is far richer, stranger, and more beautiful than we ordinarily imagine. Through Feynman's explanations, we come to see that time is both a tool for organizing events and a reflection of the universe's structure. It is a lens through which we observe change, a framework within which particles interact, and a parameter shaped by both the vast cosmos and the tiniest quantum events. By studying time, we do not just learn how to measure seconds or hours. We gain insight into the fundamental fabric of reality, the origin of causality, and the principles that govern the universe at every scale. Time, in Feynman's view, is a bridge between what we observe, what we calculate, and what the universe truly is. It is at once familiar and mysterious, measurable and flexible, personal and cosmic. Understanding it transforms our perception of reality, revealing a universe that is dynamic, interconnected, and far more intricate than our daily experience suggests.